Everyone. So, yeah, today's class, we're gonna be talking about Burnsides Lemma. Burnsides Lemma is a result from group theory, but we can apply it to certain math competition problems. So, in a lot of problems, you're kind of like asked like how many distinct something are there. So let's just look at an example. So find the number of ways to color each corner of a unit square blue or red. Two patterns are different if they can if are not considered different if one can be obtained from another by a rotation. So, we could do casework and just list them out. So if we have all red, so we can split into cases based on the number of reds. We could have four reds, in which case there's just one way. Could have three red, in which case there's one way. Could have two reds. They could be either adjacent corner-wise or adjacent diagonally, or not like kind of diagonal from each other. We could have one, in which case there's just one way. Or we could have zero reds, in which case all of them are blue. So okay, so we get six. But when the problem gets more complicated with more like a more complicated shape or more colors, listing by cases becomes a lot more tedious. So uh, Burnsides lemma, or also the lemma that is not Burnsides because everything is like not F. So Burnsides lemma says um, that the average number of fixed points, so like is equal to like so the number of like different orbits is equal to the average number of fixed points. So this is based in group theory, which we're not going to talk about. But basically, for this problem, we want to find like a symmetry of a shape is just a transformation that takes the shape back to itself. So for instance, if we have this square, a symmetry of it would be rotating it 90 degrees about the center. So then it would become one, two, three, four. Another symmetry is just to do nothing. Or we can think of it as rotating 0 degrees, but it's just doing nothing. So that's the identity. So in this problem, things uh, the only symmetries are rotation. So we can rotate by either nothing, 90 degrees, 180 degrees, or 270 degrees. So uh, so Burnside's lemma says that the number of distinct squares is the average number of fixed points. So we have to find how many so yeah, how many uh squares are fixed by each symmetry, or in group theory it's the group element of your group, and take the average of all of them. So the identity, well, each square can either be blue or red. So there's 2 to the fourth squares fixed by the identity. In a 90-degree rotation, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. So whatever color 1 is, like that has to be the color of everything. So there's going to be 2 to the fourth. I mean, there's just 2. One can either be red or blue, and that applies for all the vertices. a 180-degree rotation, 1 goes to 3 and 2 goes to 4 and vice versa. 3 goes to 1, 4 goes to 2. So there's two choices for the color. So 1 and 3 are the same color and 2 and 4 are the same color. There's two choices for what 1 and 3 could be and two choices for what 2 and 4 could be. So 2 squared. For 170, it's the same as 90, so just 2 to the first. So if we average all of these, then we get, well, this is 16 plus 2 plus 4 plus 2 all over 4, which is 24 over 4. So that gives us 6. So, we got the answer 6 in both ways, so we should be a bit more confident that our answer is right. So let's try this on an example. So number 7 says, each edge of a regular octagon is colored red or blue. Find the number of distinct octagons that can be formed. Rotations and reflections of the same octagon do not count as distinct. So I'll give you a minute to try this, and then we'll talk about it. Well, okay. So what are the symmetries of a regular octagon here, right? Well, here it says rotations and reflections count. So like there's going to be 8 rotations. We can rotate by any multiple of 45, like 0, 45 up to 315. There's also 8 reflections. We can either reflect here, 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 or here. So there's 4 reflections that connect midpoints of opposite vertices. And then there's 4 reflections that connect midpoints of opposite vertices. So in group theory, this forms a group called D8, D8, and has 16 16 elements. So, okay. So, well, we need to count, like how many are fixed by the identity, right? So, well, each vertex can be either, or each edge can be either red or blue. So there are 2 to the 8th. What about a 45-degree rotation? Well, 45-degree rotation sends this to this, this to this, and we'll just assume, I mean, like clockwise. It doesn't like, yeah. So, um, so like like this to this. So whatever the color of one vertex is, that must be the color of all the other vertices. So there's just 2 choices. What about a 90-degree rotation, right? So here, this is sent here, this is sent here, this is sent here, and this is sent here. This is sent here, this is sent here, this is sent here, this is sent here. So here there's 2 squared. So there's 2 choices for this vertex and 2 choices for that vertex. And those 2 vertices uniquely determine the colors of all the other vertices. So 2 times 2. 135 is, well, so let's see what happens in 135. So, 1 is sent to 4, 4 is sent to here, this is sent here, this is sent here, this is sent here, and this is sent here, and this is sent here, and that's sent there. So because 3 and 8 are relatively prime, this is just like rotation by 1/8 or 45. So this is just whatever the square of one color is, that's the square of all the other colors. So 2. Okay. A 180-degree rotation, well, that sends opposite pairs of vertices to each other. So that's sense there. These two are the same, these two are the same, and these two are the same. So, okay. So this is going to be, well, 2 to the 4th. Now 225, this is the same as 135, but in the other direction. So this is also 2. 270, this is the same as 90 degrees, so this is also going to be 2 squared. And 315 is the same as 45, so this is also 2 to the 1st. Okay, so now what about the reflections? Well, if we reflect here, this gets sent here, this gets sent here, this gets sent here, and this gets sent here. So that means we have 2 to the 4th. And there's 4 of them. Well, I'll let you think for a sec. What about the other type of reflection, namely about a line of symmetry connecting opposite corners? How many octagons are fixed by this? So, like the problem says how like we color the edges, but coloring the vertices is the same thing because like, there's 8 edges, there's 8 vertices, and like you can pair each edge with a vertex with an edge by just connecting the edge that's like kind of clockwise from it. Okay, so let's see here, right? We have 2 choices for what this could be. Blue, red here. 2 choices for these two. These two are the same, so 2 choices there. And these two are the same, 2 choices there. So that gives 2 to the 5th. And like I said, there's 4 of these symmetries or reflections. So Burnsides lemma says that the answer is just the average of all of these. So it's 1/16, 2 to the 8th, plus, well, we have 2 to the 2's, or 4 2 to the 2's. So 4 times 2. We have 1 to the 4th, 2 squares, 4 of these, and 4 of these. So I'll let you work out what that is on your own. Right. So let's try this problem. Number 4. So find the number of distinct patterns that can be formed by shading 3 of the 9 squares in a 3x3 grid like the ones shown below. 2 patterns are not considered distinct if one can be obtained through the other through a series of flips and/or rotations. For instance, the bottom 3 are the same. So, first off, what's wrong with this? Why, like, okay, there are 8 symmetries, and there are 9 choose 3 ways to pick the 8 symmetries. So it's just 1/8 of 9 choose 3. So the problem with this is some arrangements don't have 8 symmetries. For instance, this one is counted 8 times because any of the reflections and any of the rotations will send it to a different looking square. But this one, So this square, it doesn't have 8 symmetries. There are only 4 symmetries. For instance, the identity sends this square back to itself. A reflection over this line also sends this square back to itself. So some of the arrangements we have to divide by 4, and some of the arrangements we have to divide by 2. For instance, like this one. Uh, a 180-degree symmetry fixed rotation about the center of the square fixes this square. This reflection fixes this shape, and the identity also fixes this arrangement of 3. So, okay, so that doesn't work. So we have to use Burnsides lemma to account for the symmetries. So, well, how many are fixed by the identity? Well, that's just 9 choose 3. So now let's think. How many are fixed by a 90-degree rotation? Well, the top gets sent to the right, right gets sent to bottom, bottom edge gets sent to left. So these must be the same. The center is sent to itself. The corner, this corner gets sent to this corner gets sent to this corner gets sent to this, and this corner gets sent to this. So the corners have to be the same. So it's clear that there's no way we can put in the squares. The center can be black, but if we shade any non-central square black, then it will imply there are 3 other black squares, but we have only 3 black squares. So okay. So for both 90 degrees and 270 degrees, there are none. What about a 180-degree rotation? So, well, okay. So maybe I should read the question first. Like, find the number of distinct patterns that can be formed by shading 3 of the 9 squares in a 3x3 grid, like the one shown below. 2 patterns are not considered distinct if one can be obtained through the other through a series of flips and/or rotations. So we have both rotations and reflections to worry about. So if we reflect over this, then, well, think about it for a sec. So there are 2 cases. One is that the middle column is all black. Another is that one square in the middle column is black, and then we have one black in the left and one black in the right column. So there's 3 choices for which square in the middle is black, and then 3 squares for which squares on the left and right columns are black. 3 times 3. So all in all, in this case, there are 1 plus 3 times 3. So this applies for both like this symmetry and this symmetry. What about reflections about here? Well, this is actually the same as reflection vertically, if you think about it. Again, we could have everything along the line of symmetry is black, in which case there's one way. Or we could shade exactly one of these black, and then like we can have either these 2 black, or these 2 black. So times 3. So that's also 10. And there's 2 of these. So by Burnsides lemma, the number of distinct orbits is 1/8. 9 choose 3 plus 0. Oh, so yeah, we need to account for the 180-degree rotations. So there's going to be, well, the middle square has to be black, And then like this square gets sent to this square gets sent to this square. These two are the same, and these two interchange. So uh, so exactly two of the squares must be non-central squares, which means the middle one must be shaded. And then there are four ways to pick which pair of opposite squares are shaded. So there's four in this case. So adding them all up, you get this. So this works. This, mm, okay, it should be 128 over 8. What did I do wrong? Oh, I forgot the 4. Okay. Yeah. So yeah, plus 4. So yeah, 128. Okay, let's try this problem from the 2017 AMC 12B. So in the figure, three of the discs are to be painted blue, two are painted red, one is painted green. Two paintings can be obtained from one another by rotation or a reflection of the entire figure are considered the same. So how many paintings are possible? Well, with a lot of these, you can just do a bunch of casework and eventually get the answer with very, very careful casework. But we're going to use Burnsides lemma. So this is an equilateral triangle. So there's going to be 6 symmetries. It's these 3. There's reflection over here, and reflection about this altitude. There's also the identity, a 120-degree rotation, and a 240-degree rotation. So let's see. If we take reflection over the middle, oops, there's 3 greens and there's one line of symmetry. So like one of the greens, or there's 3 blues, so one of the blues has to be on the line of symmetry. There's an odd number of reds. Similarly, there's an odd number of reds, so the red also has to be on the line of symmetry. So it could either be blue-red or red-blue, 2 ways. Then, or okay, sorry, green, yeah. All colors are isomorphic. Yeah. So then we have 2 reds. It could be either here, 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 or here, here. So 2 choices for the reds. And then there's 2 choices for the remaining 2 blues, or just 1 choice for the remaining 2 blues. So 4. There's 3 of these, so we'll multiply by 3 at the end. Uh, with a 120-degree rotation, well, let's think, right? So this square gets sent to here. This is sent to here. This is sent to here. However, this is sent to here. This is sent to here, and this is sent back. So how many choices are there? Well, we only have 1 green. So wherever we place the green, there must be 2 other greens. So this is impossible. Same for the 240-degree rotation. So this is 0. What if we have the identity, so the do-nothing transformation? Well, in this case, it's just 6 factorial over 3 factorial, 2 factorial. 1 factorial, which is just 6 choose 3 times 3 choose 2. So overall, we have 60 plus 4 times 3, and there are 6 symmetries. Okay. So, uh, so, okay, like, yeah, let's try 13. So consider a 2 by 2 grid of squares. Each of the squares will be colored with one of 10 colors, and 2 colorings are considered equivalent if one can be rotated to form another. How many distinct colorings are there? The other. Yeah. Okay. So, like, okay, let's try this with casework, right? So what do we have? 4 distinct colors, right? Well, then there's 10 times 9 times 8 times 7. But like we have to divide by 4, I think, right? Like there's 10 choices for the first square, 9 for the second, 8 here, 7 here. But rotations are equivalent. Mm, yeah, okay. So yeah, this is going to take a bit more work. So let's just use Burnsides Lemma. Like, mm, so the identity, well, each square gets sent back to itself, right? So let's think. Each gets square sent to itself. So there's 10 choices for this square, 10 choices for this square, 10 choices for this square, and 10 choices for this square. A 180-degree rotation sends this to here, this to here, this to here, and this to here. So when I say rotation, it's always about the center of the shape because these are rotationally symmetric. But to be specific, to be precise, you should say rotation about the center. But yeah, so there's 10 choices for here and 10 for there, so 10 squared. Then there are a 90-degree rotation sends this to here, this to here, this to here, and this square to there. So that's just whatever the square of one color is, that must be the square of the remaining 3 squares. 270 is the same as 90, so that's 10. Burnsides lemma tells us the number of distinct squares is the number of fixed points, or like kind of average number of symmetries per symmetry. So this is going to be 1/4. The fourth. So if we have time, maybe we'll come back and check this with casework. Yeah. So let me know if there's any questions. Okay. So let's look at 18. So a cube is constructed from 4 white squares and 4 black squares. How many different ways are there to construct a 2 by 2 by 2 cube using these smaller cubes? Okay. So this problem requires a lot of careful casework. If you and like thinking about rotations and reflections, like rotations in your head. So it's easier to do this with Burnsides lemma. You can do it, like I've done it, but it's just not easy. Okay. So what are the symmetries of a cube, right? Well, there's the identity. You can take a connect the centers of opposite faces and rotate 90 degrees about that, or 270, but I'll just say 90 degrees. So connecting the center of the top face and bottom face. And this applies for left and right, front and back. So X, Y, Z, all three dimensions. There's three of them. And it could be clockwise or counterclockwise. So really there's six of them. We could rotate 180 degrees about these same three axes. There's three of them. There's a like if we connect midpoints or if we connect corners of opposite if we connect opposite corners, we can actually rotate 120 degrees about this. So that sends this corner here, this corner here, and this corner here. It also permutes these three corners. So there's four space diagonals, and you can rotate 120 degrees either way. So there's going to be 8 of these. You can, if we can, we can connect midpoints of opposite squares for opposite edges. So for instance, we could connect the back up edge with the front edge, down front down edge, front bottom edge. And then we can rotate 180 degrees there. That would send this to this, this to this, these two swap, and then this to this. So there's 12 edges, so 6 pairs of opposite edges. So 6 of these axes and 1 symmetry per axis. So that's going to make, like 6. There's 6 of these rotations. Okay, let's check, right? We have 6 plus 8, that's 14. Plus 3, that's 17. Plus 6, that's 23. Plus the identity, so that's 24. And are there 24 symmetries of a cube? Well, yeah, there's 4 ways you can permute these, right? There's 6 ways to choose which face goes on bottom. And then once you've chosen which face is on bottom, there's 4 ways to choose which face is front. So 6 times 4. You could also think there's 8 ways to choose which corner is the top front right corner. Once you've chosen which corner, there's 3 ways to permute which corner is to the left of it, or kind of like going this way, because there are 3 adjacent neighbors, and there's 3 ways to orient them, fixing that corner. So 8 times 3. You could also think there's 12 ways we could put this edge. Maybe it's the front, maybe that edge gets sent to the front top. Once you pick that edge, you can rotate this edge 180 degrees about its midpoint to orient the cube in 2 different ways. So it's also 12 times 2. Okay, so regardless, there's 24 symmetries, and we've accounted for them all. So I'll give you a minute to try this, and then we'll talk about it. Okay, let's talk about it. So let's see. This time we have a fixed number of like white and black squares. It's not just every square can be any color. And we had the same thing with this AMC 12 problem too. Like there were only like yeah. So well the identity fixes 8, choose 4 of them, all of them. How many squares are fixed by a 90-degree rotation, like about this, an axis connecting midpoints of opposite faces? Well, this square gets sent to this cube gets sent to this cube, this is sent here, and this is sent here. Similarly, the bottom 4 faces are all the same as well. So there's 2 ways to do it. Either the top is black and the bottom is white, or the bottom is black and the top is white. So 2 there's going to be. What about a 180-degree rotation? Let's see, right? So this cube gets sent to here. This cube gets sent here. These 2 cubes swap, and these 2 cubes swap positions. So that's going to be so we have 4 total blacks and 4 whites. So there's kind of 4, like we need 2 of the sets to be black and 2 of these like sets to be white. So there's 4 choose 2. What about space diagonals, rotations? Well, so rotation about the space diagonal. So let's say it's about this space diagonal. This can be anything. This can be anything. So, well, not anything, but like, so these 3 vertices, they or these 3 cubes, they like form an orbit. So like they are interchanged with each other. Same with these 3 cubes adjacent to this corner cube. So there's kind of 4 classes that these unit cubes are separated in. The front, right, left, bottom cube, the back, right top cube, and these 3 and these 3. They form an equilateral triangle. So these 3 cubes actually, their centers form an equilateral triangle. So we have 4 blacks and 4 whites. So it must be that like one of these sets of 3 is black and the other is white. And one of these like solo like cubes, like one of these like individual cubes is black and the other is white. So there's two times, therefore there's two times two. There's eight of these. There's, so if we look at rotations about an axis connecting midpoints of opposite edges, then uh, it will, like, this square gets sent here, this cube gets sent, I mean, like, this cube and this cube swap, this cube gets sent here, and this cube gets, yeah, it gets sent there. Yeah. So we have four classes of cubes. So like and we have four black, four white. So there like two of them have to be black and two of them have to be white. So two times two. So adding these up, we have 124. So there were then uh so 2 times 6, 6 times 3, so 12 and 18, that makes 30. 30 plus 32, that makes 62. 62 plus 24, that makes 86. So, uh, mm, wait, I think, hang on. Wait. Oh, I worked this out earlier, but yeah. Oh, my bad. Yeah, there are four sets of two here. So this is four choose two. I mean, yeah. So and there's six of them. So uh, yeah, it's probably a bit better to write some of these as four choose, as like leave them as binomial coefficients. So okay, so this makes 30. This makes 62. Th 36 plus 62 is like 98. So 70 plus 98 is 168. Yeah. So if you know the symmetries of a cube, this way is actually easier and less likely to make mistakes. You just have to be more careful than me. Uh, uh, okay, so let's take a 5-minute break, and then when we come back, we'll do a few more problems. Resume. So let's solve the cube problem in general. Let's say we're coloring the vertices of a cube. So how many ways can we color it with n colors? So this is a function of n. Well, by Burnsides lemma, it's an average over like a number of orbits. So the yeah, so if we do nothing, then all 8 vertices are fixed. So there's n to the eighth. If we have a 180-degree rotation about an axis joining midpoints of opposite faces, so well, this gets sent here, this gets sent here, this cube gets sent here, and so on. So like there's going to be like so these four vertices are the same color, and by the similar reasoning, these four are the same color as well. So n squared. There's if we have a 180-degree rotation about this axis, then this gets sent here, this gets sent here, this gets sent here, and this gets sent here. So it's into the fourth. It's 3v. If we have a 120-degree, like for the 120-degree rotation, um, let's see here, right? The corners are so this is about a space diagonal connecting opposite corners. Like the corners are can be any color, so n squared. And then like these three vertices have to be the same color, and these three have to be the same color because this gets sent here, this gets sent here, and this gets sent here. So this is and similarly for these three. So this is n to the fourth. There's 8 of these because we can, again, we can rotate either way about the space diagonal, and there's 4 space diagonals. If we connect midpoints of opposite edges and do a 180-degree rotation about this axis, then there's yeah, so these two vertices are the same, these two are the same, so n squared, and then these two are the same, and like these, like, yeah, it's kind of hard to draw, but these two are the same. So like uh yeah, there's going to be n to the fourth. So overall, we have uh so 6n squared. Wait. Yeah, I think this is right. Uh, okay. I think I may have a stake in my handout. So, okay, let's try number 10. So Edward places 7 beads on a bracelet chain, then ties the two ends together. The beads are identical except for color. If 3 of the beads are red, 2 are green, and 2 are blue, how many distinct bracelets are possible? So rotations and reflections are like considered equivalent. Okay. So this is like, so we have 7 beads on a bracelet. So this is D7. Like you can think of it as a regular 7 gong where we can like reflect and rotate. So like if we do, so let's use Burnsides lemma. Like if we do nothing, like in our intermediate counting class, we do this just by hand, but let's do it with Burnsides lemma. So uh like the identity is this will fix 7 factorial over 3 factorial, 2 factorial, 2 factorial. Just And then let's see, if we rotate by 1/7 of a circle, so this goes here, and so on, then this will fix like not like everything has to be the same color, but we have 3 different colors. So all of those will fix 0. And it's the same for 2/7 of a circle and 3/7 of a circle and any like k/7 of a circle. So okay, so there's 0 with like for 6 of the symmetries. Then, um, like we could reflect, right? So how could reflecting give us back what we want, right? So uh, we have 3 red, 2 green, 2 blue. Well, uh, if we cut the bracelet and put them in a line, the only way to have a line of symmetry is if we have an odd number of red and even number of green and blue. So the only way to have a like symmetry is like if the middle one is red. So then there's has to be 1 blue, 1 green, and 1 red on either side. So 3 factorial ways. That's true for any of the line of symmetry. Like we could rotate this by 1/7 of a bracelet circle and then just like, yeah. So there's going to be 6 ways, and that's for all 7 rotations. Like we could make this the line of symmetry, make this the line of symmetry, and just kind of rotate the bracelet, Yeah. So this is 6 times 7 is 42. So there's 7 rotations and 7 whatchamacallits? Reflections. So 14 total, and this will give, so 252. Okay. So it's a bit trickier to think of. I mean, you can do this like another way too. Uh, so like the other way to think about this is like yeah, there is another way to think about it, but okay. So okay, so let's look at this problem from the USAMTS. So you have 27 unit cubes. They're in a 3 by 3 by 3 cube, and 25 are black, 2 are white. How many distinguishable cubes can be formed? Hmm. Well, so this is Burnsides lemma again. We can use Burnsides lemma again. So let's see, right? I'll give you a minute to work on it, and then we'll talk about it. So, okay, let's talk about it. So the identity, we'll use Burnsides lemma. The identity fixes 27, choose two of them. Um, a space diagonal 120-degree rotation about a space diagonal. Uh, well, okay. So this partitions the cube into sets of three. Like the order of this, we say the order of this group is like three, or this element is three. So the only way two of them can be white is if they're all on the space diagonal. So there's three, choose two ways. If we reflect over midpoint, like rotate 180 degrees about axis, like this axis, joining midpoints of opposite edges, then, well, I mean, it's the same, like, so there's two cases. One is if they are like all three on that diagonal, or there's 3 cubed minus 3, choose 2, each is 24 cubes off the axis of rotation. So these can be paired into 12 sets of 2. So there's going to be like, so each of those pairs have to be the same color. We could have we could have one cube on the axis of rotation and one set off the axis. So it's 3 times 12. If we rotate 180 degrees, okay, well, I'll let you think about this for a minute. So how many ways are there to do that now? So yeah, so for a 180 degree like ro rotation, we could have all three on the axis, or we could have one on the axis, and then there's 24 off the axis. So it's like the same as this one. So plus. Uh, oh, so sorry. There's two white cubes. Yeah, I'm mixing this. Okay, with the Yeah. So this is th three choose two if they're both on the diagonal, or just 12 if they're both off. So yeah, 15. And this is three choose two if they're both on, and uh t t like 24 over 2 or 12 if they're both off. Okay. Okay. So so uh there's if we do a 90-degree rotation, well, now every cube is like most of the cubes, every cube not on the axis of symmetry is sent to like three other cubes over the course of its orbit. So yeah, it's going to be like, so both of them have to be on the axis of symmetry. So three choose two. And there's oh yeah, and so there's that's so there's eight like this. There's six like this. Uh, three and six. Three like this and six like this. So, okay. So this is, well, so 6 times 15 is 90. Uh, 15 times 3 is 45. And 6 times 3 is 18. So if we add this up, so if you work this out, this should be 22. Okay. So let's try one of these problems with casework, like like this cube or this grid of squares one. So there's a few cases, right? Like so one is if they're all different. So if we have four distinct colors. Okay, I don't know what's wrong with my, okay. So uh, if we have four different colors, okay. Another is that we have three colors. So we have like two of one color, one of another, and one of another. If we have two colors, then like we could have two and two, or we could have two of one and two of another, or we could have three color, like three of one color and one of another. If we have, and we could also have one color. So uh, if we have two of one and two of another, then they can either be the two that are like diagonal, that are the same, or the two that are like adjacent, that are the same. Okay. So uh like how many, okay. So uh if we have four different, there's nine times eight times seven times six. Because there's 10 ways here, nine ways here, eight ways here, seven ways here. But like another way to think about it is it's 10 choose 4 times 4 factorial. Oh, maybe I said the wrong thing, but yeah, 10 times 9 times 8 times 7. If they're all the same, well, that's easy. Then like there's just 10 ways. If three colors, it has to be 2, 1, 1. So the two that are the same, they could be on adjacent or adjacent corners or opposite corners. If they're on opposite corners, there's 10 ways for the color of these two, 9 ways for the color of this one, and 8 ways for the color of that one. But there's two ways we could like choose which two are the same, either these two or these two. So that's like 9 times 8 times 7. So if they're on adjacent corners, then there's 10 ways to choose the color of these two, 9 ways here and 8 ways here. But the two adjacent ones can be like one of four ways. They could be the top two, the right two, the bottom two, or the left two. So um yeah, that's going to be 4 times. If we have two of one and two of another, then like if they're if they're paired by corners, so like if it's the corners that are the same, then there's just 10 ways for this and 9 ways there. But I mean like rotations are the same, so it's really just 10 choose 2. 10. Oh, sorry. So like because these are rotationally symmetric, it should be 10 choose 4 times 3 factorial. So yeah, what I said earlier was like it is 10 over 4. Yeah. Because for any coloring like red, green, blue, purple, uh you can rotate it 4 different ways, and then so we've overcounted by a factor of 4. And then it so if it's 2 and 2 this way, so if like kind of adjacent ones are like uh the same, then like there's 10 ways to pick this and 9 ways to pick this, but that overcounts by 2. So there's also 10 choose 2. And then yeah, we've already done if they're all the same color. So like let's compute. So 10 choose 4 times 6. So like but both of these are 9 times. Okay, so let's Yeah, so this is 210. We can factor out 10 times 9 times 8. This just becomes 90. It's 10 times 9 and plus 10. Okay, so we got 2530 earlier. Yeah. What did I do? Oh, okay. So like, yeah, so we have to count for rotational symmetry. So like when we have 211 and these two are the same, for instance, like we only have to pick which two are the same, and then it's just 10 times 9 times 8. And then these two is also 10 times uh, yeah, when opposite corners is also just 10 times 9 times 8. Like because uh like basically it could be any like yeah, so when the opposite corners there's 10 choices for them and then there's 9 and then there's 8. So yeah, it's just so, so this is uh, okay, so we got 2530 for this earlier. Oh, this is times 3 factorial. Yeah. So I forgot that. Yeah. So this is yeah. So uh, uh yeah. So okay. This is still not right. So let's see. There's uh 10 10 choose 4 times 3 factorial ways here. Oh, okay. Yeah, so when these are diagonal, you have to divide by 2 because like we could flip this 180 degrees about the center and then these two like would switch places. But those are considered the same since rotations are the same we're like yeah, rotations are symmetric. So this is 10 times 9 over 2. So okay. Yep. So 1/2. And this is minus 1.5. And so, yeah, I can't do computations anymore. So, yeah. Uh, this still is at 2530. Okay, so this is so if it's on an edge, it's just 10 times 9 times 8. 2 and 2 could be, so if they're adjacent corners, and if it's like this, then it's 10 times 2. Oh, maybe, oh yeah, we didn't do 3, 1. So if it's 3, 1, then it's just 10 times 9. Yeah. And then if it's 4, it's 10. Mm. So like it's 2 times 2. Yeah, we shouldn't, we should leave the computation till the end. So, okay. Uh, okay, yeah. So we get to 2530, which is what we got earlier. So yeah, like this is why uh you should, like, Burnsides lemma can kind of help avoid all this casework and thinking about symmetry. We haven't proven Burnsides lemma, but like, yeah, like it can, yeah. So let's do one more. Oops. I don't know what I press. What do I do? Okay, I'll just ignore that. Okay, so uh, Wally's keychain makes and sells 2 types of keys. Mr. Porter buys a total of 12 keys from Wally's. Determine the number of arrangements of Mr. Porter's 12 keys. The rotations are considered the same. So let's use Burnside's lemma. Well, I'll give you a minute to try it, and then we'll talk about it. Okay, so let's talk about it. So we can use Burnside's lemma. So there's 12 rotations. Let's see. Uh, every key can be one of 2 types. So the identity will, there's 2 choices for each key. So the identity will fix all 12 keys. So there's 2 to the 12th. if we rotate by 1/12 of a circle, so let's say 30 degrees or 1/12, then it will be like, then like every key goes to the next key, so they're all the same. So 2 to the first. So 0 is the same as 1 is the same as 2, all the way up. Uh, if it's 1/6 of a circle, so a 60-degree rotation kind of, then it's just 2 squared because all the even number keys are the same and all the other odd number keys are the same. So it's like there's two sets. It's like every other key and every other pair. If it's rotating by 3 keys, now there's going to be 2 to the fourth because yeah. Uh, because like, okay, so if we arrange the keys in the order of like a clock, then like 12 o'clock goes to 3 o'clock, 3 o'clock goes to 6 o'clock, 6 o'clock goes to 9 o'clock, and 9 o'clock goes to 0 o'clock. Similarly, 1 goes to 4, 4 goes to here, and like 7 goes to 10. Similarly, all the 2 mod 3s map to each other. So there's going to be 3 sets. Uh, oh, okay. So what I was saying was for the next one. Sorry, I got ahead of myself. This is like that's for 4. So for 4, there's 2 cubed. Yeah. So for 3, like tw 12 o'clock goes to uh 4 o'clock, 4 o'clock goes to 8 o'clock, and 8 o'clock goes to 12 o'clock. Similarly, all the 1 mod 4s go to each other, all the 2 mod 4s go to each other, and all the 3 mod 4s are in the same set. So there's going to be 4 classes, and each one can be one of 2 colors, red or blue, or like one of 2 types. So 2 to the fourth. Yeah. So if there's 4, if we're rotating by 4 keys, then like 12 is the same as 3 is the same as 6 is the same as 9. And like 1 mod 4s are the same, 1 mod 3s are the same, and 2 mod 3s are the same. So there's 2 times 2 times 2. 5 is 5. Well, what about 5, right? So 5 is relatively prime to 1, I mean to 12. So like 12 will go to 5, which will go to 10, which will go to like, yeah. So if you've ever done problems of the type like, um, oh, like I count by fives, like Misty counts by 12. So what's the first number that like we agree on, a positive number that we agree on? Well, like the multiples of 5 and 12, they're like disjoint up to 5 times 12. So yeah, like 5, because 5 is relatively prime to 12, like one, like the multiples of 5 will hit everything mod 12. So there's going to be just one set, so 2 to the 1. So there's 2 ways to color it. If we rotate, yeah. So 6. If we rotate by 6 keys, then uh like the opposite keys are the same. So there's 6 pairs and each of them has 2 choices. Now like we can use like symmetry, right? Like by symmetry, 7 is the same as 5, 4 is the same as like 8 is the same as 4. 9 is the same as 3, 10 is same as 2, and 11 is the same as 1. So okay, so we can pair these up. So the answer is just, well, okay, so like I'm going to write it out because it's like a bit more proper or like good to write it out. But like, you could just double some of these. Yeah. So I'll let you compute what this is. Like, yeah, it turns out it's 352. But yeah. So one thing that's interesting about Burnsides lemma is like it gives a lot like this is an integer. If we compute this and it's not, then we've done something wrong. So like, yeah, so like this gives some sort of weird, like interesting congruence modulo 12. Because this is an integer, it gives an interesting congruence mod 12. Okay, so let's just do one more. So like uh it's not so well, okay, so I'll just type it. My computer is being very slow. Like how many ways can you color the faces of a cube up to rotational symmetry? So earlier we did the vertices of the cube. Now we have to do faces of a cube. So let's say with n colors. So this is with n colors. So uh well, how many ways? So like yeah, there's six faces. The identity will fix n squared, right? So or n to the sixth. If we take a space diagonal, so for rotations about the space diagonal, like uh, the front, the left, and the bottom are the same, and right, top, back are the same. So that's two classes. So like, yeah, like n squared. Mm, and there's eight of these. Like for like if we rotate about a vertical axis, then the top can be n, the sides can be n, and the bottom can be n. So n cubed. So if we rotate uh 180 degrees about the vertical axis, then the front and back are the same, the left and right are the same, the top can be anything, and the bottom can be anything. So there's n choices for the top, and for the bottom, and for the left, right, and for the front and back. So and what if we rotate about so okay, so midpoint of opposite edges? Well, let's think about this, right? So now the top and the back are the same. The front and the bottom are the same. Uh, like, and the left and the right are the same. So n cubed. So this has, yeah. So this will give, um, so by Burnsides lemma, there are 1 over n to the 6 plus 8n squared plus 4 plus So uh, like we can combine these, but yeah. So I encourage you to like try some of the problems we've done and do them without Burnsides lemma and see like which way do you like better. Mm. Like just to give a sense of like how we might prove Burnsides lemma. So like I'll just state the definition of a group. You don't have to take this too seriously for now. So a group is like a set S uh, with a binary operation star such that like if A and B are in S, then A star B is in S. There is an identity. So like there such that like like an identity in S, an element called the identity, such that like the identity times anything equals anything times the identity equals A for any A in S. So uh so three, there is an inverse. So for all A in S, there is an element A inverse in S, such that A inverse star A equals A star A inverse equals the identity. And yeah, or like it's so the identity like so like the operation is like associative. So A star B star C equals A star B star C. Yeah, so these are stars. So you can check that all the symmetries we've done so far satisfy the definition of a group. And the like the statement of Burnside's lemma is like in terms of groups. So basically it's like if you apply an element over and over again, you get what is called as the orbit. So orbit of A is like A, like yeah. So like really the like this is on group actions. So you apply uh the set of a group on a set. So like so this is like G cross like S or something. So like the elements of G, so these are pairs GS where this is a group element and this is an element and S is an element of your set. So this yeah, so here maybe our set is all colorings of a cube or like a particular like all six like colorings of a cube with a certain number of colors. And G is the set of like big G is the set of symmetries of a cube. So like, if we rotate by 90 degrees about this axis, like a vertical axis connecting midpoints of opposite faces, then it like we can apply this group to the set. Like the set of all cubes under the group action under one element is called the orbit of the group. So if we take like a 120-degree rotation about the axis of like a space diagonal of a cube, then like the orbit is like this gets sent to this gets sent to this. So like uh yeah, if you take some coloring of the cube, the orbit is just like all the things it can map to under that group element. So yeah, so like a fixed point is called uh so a point is called fixed if the like group element acts on it like the identity. So for instance, if the front is red, the bottom is red, and the left is red, and then like the right is blue, the top is blue, and the back is blue, then a 120-degree rotation about this space diagonal will set like this cube is a fixed point of that transformation or that group element. So because this blue gets sent to this blue, the top blue face gets sent to the back blue face, and the back blue face gets sent to the right blue face. Whereas and the red front gets sent to the red. So like yeah, so like the cube looks the same before and afterwards, so it's called a fixed point of the group of this element of this element. And like here, like our group is a set, and the set is all symmetries of the cube. So the elements of our group are the symmetries of our cube. So like yeah, so like Burnsides lemma says the average like the orbit is the average number of average it's like 1 over the size of the group of sum of like fixed x or the size of fixed s as x ranges over the group. And this is uh like the number orbits yeah is that. So here the orbits are kind of like how many distinct cubes are there. So okay. So I'll just say colorings in this, yeah. And then the fixed, like the number of fixed points. So this is over all symmetries like in the group. Like this is over all, yeah, like the set of symmetries in our like problem or something. Yeah. So uh, yeah. Like if you want to learn more about group theory, I encourage you to do so, but there's no rush. It's typically taught in the first year uh algebra class in college. So like but group theory is useful for like chemistry and um like it's useful for a lot of things. So yeah, like even if you don't end up studying mathematics, it can be used in a lot of other fields.